So into our last lesson of quantum mechanics, the topics I want to get to is electronic configuration and orbital diagram, which is all based off the quantum numbers. I've got two charts up. The first is the energy of different orbitals for a one electron system is first. This would be something like hydrogen. So if you study the Balmer series of hydrogen, this is what you're going to see. Nothing to really memorize here. All these subshells are all at the same energy level. So there's only one type of S. All the P's, the 2S and the 2P's are all at the same energy level. All three of the S's are at the same energy level, and all four of the D subshells are at the same energy level. So in something like the Balmer series for hydrogen, if an electron goes from the second energy level up to the fourth, it doesn't matter what subshell it goes to, they're all the same energy. And when an electron falls back down from 4 to 2, it doesn't matter what subshell. You're going to have the same drop, you're going to have the same energy, and you'll have the same wavelength. So the red line is the 3 to 2, the 4 to 2 is the green line in the Balmer series. Okay? So subshell doesn't matter in one electron system. In more than one, so 2 electron plus systems, every subshell is not at the same energy. So you need to know the fill sequence of all the different subshells. But our periodic table is going to tell us this. You don't really have to memorize it. But it fills, the 1s will fill first, then the 2s. That's first, that will fill second. That would be 4 electrons, 2 and 1s, 2 electrons and 2s. Then you'd start filling 2p, and that would be third that you'd fill, and that would hold 6 electrons. And if you have more electrons in the system, you're going to move on to 4s. And then you go on to 3p, and you keep filling your way up. You'll find that it isn't just by principal quantum number when you do the filling. 3d doesn't fill after 3p. 4s is actually of lower energy before you get to 3d, which seems confusing, but when you relate it to the table, it all makes sense. So I want to relate that to a table, this ordering, and why you don't need to memorize this. So here's a periodic table. You're always going to have one. At the very start, if you have a 1 electron system, you're filling up 1s to start. And it's best almost to think of helium being over here. In terms of quantum mechanics, helium is better thought of as in the s block above beryllium. So your first electron will be hydrogen. Helium is a 2 electron system. You put 2 electrons into that 1s orbital to spin up and to spin down. What comes next? Lithium, beryllium. This is 2s. That's what you're going to start filling. This is all the s block. Got the P block here, not including helium. Okay. Helium is in the S block. In our tables, we put helium over here because of its inert gas properties, okay. But it's not in the P block. So we got 1s, 2s. What comes next? 2p, and that's the ordering we saw before on that. There's our 1s, then our 2s, then we jump over to 2p. 3s is next. And there's 3s in our table. What comes next? 3p. What comes next? 4s. Remember that D was kind of out of whack? It didn't seem like it was in the right place. So we have 1s, 2s, 2p, 3s, 3p, then we hit 4d. That's exactly what we hit when we snake our way through the table. So I just finished at 4s, and 3d is next. So here's 4s, and after 4s is the first time we hit the transition block. This is why scandium isn't put a row higher, is because it's the element that comes after calcium. So that's its place. So got our D block. And this is actually 3D. It's in the 4th row of the periodic table. After 3D, what comes next? Well, you just follow through the 3D and you're back in the 4P, and that's what comes next. After we finish krypton, we're now down here and we're in 5s. What comes after 5s? Well, we're back in the D block, but it's one number lower than expected. The D block is offset by 1. So the 3Ds show up in period 4. That's what I mean by offset by 1. I'll stop soon, but I'll do a little bit more. So after 5s is 4D. After 4D, we're back in the P block, and the S and the P's follow the row count. So 5P, what comes after 5P? It's 6s. 5D. 6P. So if you just keep snaking your way through the table, you get that fill order. No reason to memorize it. And we're not going to go down and get F block type questions with the same pattern would work. The problem is our periodic table isn't really a flat projection. It's not the best projection. The F block actually fits in there. The best periodic table probably wouldn't be flat. If you Google different projections, there's lots of them. I think one of my favorite is a spiral. Probably the best periodic table. You take your table, you line up one side with the other, offsetting it properly, and it just keeps flowering around and around and around. 1s, 2s, 2p, 3s, 3p, 4s, 3d. There you go. So that's the fill order from lowest energy first. If you only have 2 electrons in the system, it's not going to fill 7f first. It's going to start at the lowest, 1s. Okay, so that's the patterns I'm going to use. You may want to make a note of that. Maybe you'll just remember that pattern going through your table. And that's going to be really handy for answering questions. We're going to look at kind of the long way for the last time. We're going to look at all the quantum numbers in beryllium and then jump into some shortcuts. And the table will be our friend. We don't even need to look at quantum numbers to do electronic configuration or orbital diagrams. It'll be at the bottom. One last example of all of those quantum numbers. So I'm going to do the quantum numbers for all electrons in beryllium. And one big principle that I'm using is the Pauli exclusion principle, which says no 2 electrons can have the same quantum numbers. So 2 electrons can't be n equals 1, L equals 0, and L equals 0, and they're both spin up. They're both plus half. That's not allowed. If once we go spin up or plus a half of 1 electron, we can never use that unique set of quantum numbers again. The next one will have to be the spin down. Only one number has to be different. So we have to start at the first energy level. And I'm doing the very first electron. I don't have to do the second, the third, and the fourth. So I'm going to be going quickly through all those rules we got in the previous lesson. N, it starts at 1. L starts at 0, goes up to n minus 1. And L is plus or minus L. And MS is the plus a half, the minus a half. So our first electron, L equals 1. Sorry, N equals 1. L is going to have to be 0. That's an s orbital. There's no other L allowed. ML, I have no choice. Plus or minus 0, there's only one option. We get to MS, and now there's two options. I have to pick one. I'll do the plus a half for my first electron. Now in my mind, I'm like, okay, I've got another MS option. I've got the minus a half option. So for my second electron, I'm going to stay in the first energy level because I haven't filled it yet. I'm going to stay in S, and I'm going to stay in that same only orientation of S, and I'm going to put my second electron, the minus a half. I've not violated the Pauli exclusion principle because they're unique sets of numbers. They're not identical. There's a difference between the first and the second electron. So both of those electrons are in n equals 1. They're both in s orbitals. And the short form we're going to use to describe both of those electrons is to say that there's two electrons in that orbital. So instead of writing out the minus and plus a half, we can just use the 2. Now we're not supposed to say squared, we're supposed to say 1s2. There's no vocabulary test, but don't go off to university and embarrass your teacher and say 1s squared. That's not how you're supposed to say it. 1s2. Now beryllium has 4 electrons. It's atomic number 4, so we have to keep going. There are no more possible quantum numbers allowed for n equals 1. We can't have n equals 1, L equals 1. There's no p orbitals. So we've got to move to n equals 2 for our third electron. L equals. Now 0 and 1 are both allowed, but we have to start at the lower energy version first. So 1s, 2s comes next. 2p is of higher energy. Don't write this. There are two options, the s and the p. The s is lower energy, the 0 is lower energy, the 1 is the p is higher. So I have to start with the lower, the 0. And L, well, for L equals 0, there's still only one option. There's only one orientation of a 2s orbital. I need an electron. There's two equal energies, the plus and the minus a half. I'm going to pick the plus half. That's our third electron. We need a fourth. We're going to keep building up from the bottom. We did not fill that 2s orbital. We only put one electron in, so we can put a second electron in that orbital. So same orbital. These numbers are the same, so it's the same orbital. There's a different spin down electron. Electrons 3 and 4 are in the second shell, the s subshell, and then there are 2 electrons in the in that s subshell. We're good at the Pauli exclusion principle. So what is the electronic configuration for beryllium? It's those short forms. The first 2 electrons are in the first energy level, S subshell. There's 2 electrons. Second 2 electrons are in the second energy level, the S subshell, and there's 2 of them. And that's it. That's the electronic configuration. That's what we really need to understand chemical properties, bonding. Next week, we'll look at making ions and taking electrons away, and we're just going to start with electronic configuration and take away some electrons starting at the highest energy. So that's electronic configuration. We'll see lots more examples of that. So that's one way we can represent all those quantum numbers really quickly. To get that from the periodic table, we could also get that really quickly from the location of the table. Here is beryllium. Where is it in the table? It's after hydrogen and helium, which is 1s, and that's 2 elements. Now we're into the 2s block, and beryllium is 1, 2 over. So I need 2 electrons. So just the position of the table. I'll do this more. You'll see many more examples, but the location of the table can give us electronic configuration. You're going to see all kinds of patterns. You're going to see everything in group 2 and in S2. You're going to see everything in group 3 and in P1 because it's the first element in the P block. So I can mark stuff quickly, and you can double check your work really quickly once you have all the patterns. Because if you did bromide for me, it's in the P block, and it's the 5th one over, so I'm going to expect P5 to be the ending of your electronic configuration. Every halogen ends in P5, and that's why they have similar chemical properties. Orbital diagram, and then we'll do another electronic configuration and another orbital diagram. The orbital diagram, every orbital is going to be its own box. If we've got 3 P's, we need 3 boxes. 5 D's, we need 5 boxes. Every orbital is a box. What is the very first orbital that we have? What's that lowest energy one? That's 1s. Now I'm still doing this for beryllium. That's our heading. We've got 4 electrons. The very first orbital is 1s. I can do the spin up plus a half, the spin down minus a half. That's the first 2 electrons in beryllium. I need 2 more, so then I move to the next energy level. So 1s is done. Next in our table is 2s, the lithium and beryllium section. I've got 2 more electrons to put in. Spin up, spin down, done. That's the orbital diagram for beryllium. So hopefully things are getting a little simpler, not more complex. You might need to practice, you might need to get more comfortable, but we're trying to use short forms, visuals for quantum numbers. So we're going to move on, oxygen now, same thing. I have nothing really new to introduce in the rest of this lesson. So we do the electronic configuration and the orbital diagram for oxygen, and we're not going to do quantum numbers. Okay? It's going to get worse. We're up to 8 electrons now, so that would take us a long time to describe every single electron. And we're only at 8 atomic number-wise. We've got to leave that behind. So what's the electronic configuration? We've kind of talked a lot about 1s is first. Uh, 1s can hold 2 electrons. And we have to realize oxygen is atomic number 8. So there's 8 protons, so there'd be 8 electrons in neutral oxygen. So we've got to keep going till we get to all the powers being 8. For the superscripts being 8. Next is 2s. 2s can hold 2 electrons. We saw that in beryllium. That's filled. We did the spin up and the spin down. Now we got to keep going. What comes next? So we did 1s. We just did 2s. And now we're starting into that 2p block. We're into p orbitals, and there's 3 of them. And they can each hold 2 electrons. So 2p, we can put 6 in it. But 6 would fill the whole thing. How many more do we need? We want 8 for oxygen. And we've done 4 already. So we need 4 more P's. And that will give us our 8. Now, if you just count in your table, where's oxygen? There's 1 p, there's 2 p's, there's 3 p's, there's 4 p's. I knew it was going to end in P4 before I even started the problem, due to the pattern of the table. So that's the electronic configuration for oxygen. Let's do the orbital diagram. Orbital diagrams are going to expand those p orbitals out into 3 boxes. So we've got something to deal with. We've got 1s, I'll fill that in a second. We've got 2s. And then when we get to 3p, there's the px, the py, the pz. You need to realize there's 3 different orbitals, and we show them all in orbital diagrams. So it's a little more complex than electronic configuration, where we just lumped everything together. We didn't worry about what was spin up and what was spin down, or plus a half, minus a half. So our 1s orbital is filled, 2 electrons. Our 2s orbital is filled. Our p's have 4 in total. So we actually have several options of how we fill them. But we've got a quantum mechanical rule that tells us how we have to fill them. The most stable arrangement, and that's what we're trying to do, start with lowest energy and build up, of a subshell. So we're looking at that P subshell right now, and the most stable arrangement is the one with the most parallel spins, or the same spin, same arrow. So we want to maximize the same arrow. We're going to go up, up, up as long as we can. After we've done as many ups as we can, we'll go back and do the downs. So we've got 4 electrons left. There's 1. There's 2. I went parallel spin. They're both up. I've got 2 more. There's my 3rd. Okay, I'm maximizing the parallel spin, or pointing up. And then last, I've got a 4th one, and I have no choice now but to do an opposite MS and do spin down. So that's the correct orbital diagram. This matches the observations we see for oxygen. Magnetism is an offshoot of, do we have single electrons or not? Or do we have everything paired up? So a couple, there's many different types. We're not doing ferromagnetism that maybe you're used to with magnets and iron being ferromagnetic. The 2 other definitions, paramagnetic substances, which are attracted to a magnetic field. Aromatic substances have unpaired electrons in their orbital diagram. Dimagnetic substances, which repel magnetic fields, have all electrons paired. The bottom's repelled. So this will be a typical question. I can test to see if you understand the orbital diagrams. If you went with oxygen and went paired in the 3 P's, you would get the magnetism part correct. Oxygen has 2 unpaired electrons, so it is a paramagnetic substance. You don't necessarily have to do electronic configuration or orbital diagrams to figure this out. Our table helps us. Anything that's a noble gas is going to have all the orbitals filled up. Any of our halogens, fluorine, chlorine, bromine, iodine, all of those are going to end in P5. If anybody pair up an odd number of electrons, good luck. You can't pair up odd things. So our group 5, group 4, we're going to see a pair and 2 singles in the P's. Nitrogen, so oxygen is group 6, nitrogen group 5, we're going to have 5 electrons in the p orbitals. So you can look at the table and potentially figure out whether they're all paired or not. Look at something like beryllium, it's filled up the s block. Group 2, you've filled up that s orbital, 2 electrons, so they're all going to be paired up. Beryllium, magnesium, calcium, strontium. A couple more examples, then I'll be done. So I do have just a mislabeling. Just going too fast or thinking about too many things. I should have stayed in the 2s. So last slide on this theme. And I'm going to now try to use all the patterns, do these as fast as I can. What's the electronic configuration? Orbital diagram for these 3. I'm going to start with carbon. I'm going to flip back to my table with carbon, and then you're going to have to follow along with the pattern without me flipping back. So fill that in a second. Clear my table. So carbon is here. That's in the 2p section. It is what? 1, 2 over in 2p. So that's going to be my ending. Okay. I'll do lithium later. It's going to end in S1. And calcium is my last example. It's going to end, this is the 4th row, so it's going to end in S2. Will be my ending. I'll just snake my way through the table. So carbon, we're ending in the 2p's. So no quantum numbers at all. We're not even thinking about those 4 numbers. We're starting at the bottom. 1s, 2 electrons, 2s, 2 electrons, 2p. It's the second one over in the p block. So it's 1s2. I didn't even look at the atomic number of calcium. I didn't even look up its atomic number 6. But it all worked out to 6 electrons by the position in the table. Super fast. So this is where things are starting to come together. And in university, you can forget all about the quantum stuff, but hopefully electronic configuration can come back fairly quickly. Lithium. Okay. Now you may want to look at a table, find the spot of lithium in period 2. 1s2 would cover the first shell. We're in the second shell. S block, it's the very first element, so it ends in S1. It has everything that's a alkali metal, ends in S1 and is super reactive. It wants to lose that S1 electron really easily. Calcium, we got to snake through a lot of the table now. So maybe follow along with your finger as I snake through. 1s2 is hydrogen and helium. 2s2, lithium and beryllium. Now I'm into 2p at boron, and that holds 6 electrons to go all the way over to the noble gas. Now I'm dropping down to sodium, 3s, 2 electrons. We didn't get to calcium yet. We got to go through all the 3 P's. And we're finally getting close to calcium. We just went through the 3 P's to argon. We got krypton and calcium in the 4th period. Period 4, S block, second one over, we're done calcium. And again, I didn't even count. I know calcium's atomic number 20, and that those numbers should add up to 20, or I made a mistake writing them out. So that's our kind of configuration. Imagine how this is so much easier. You know, if you get down to lead, it's not that bad. It's going to take you a little bit, but you need another minute to snake through the table and get there. So we've got a bunch of orbital diagrams to do. I think I'll just do the first 2 because calciums will be bigger and probably not more educational. I want to do something you'll see sometimes. For the 3 P's, I'm going to do a big rectangle and just divide the box up. But I still have, for those P's, 3 different boxes. So 1s, 2s, 2p. My brain wants to write 3p, but it's wrong. 2p. We got to do parallel spins until we fill the box. So 1s is all we have at the lowest energy. 1s, we're going to fill our 2 electrons. We move to 2s. Okay. 2p is a different energy. So I'm putting some dashed lines just to separate out visually the energies. Okay. You don't have to put the dashed lines in your answers, but you got to fill all the boxes to get to a different energy. 2 electrons. Now we get to the 2 P's that are all at the same energy. We've got 2 electrons. We have to do parallel spins first. When we get to bonding, pairs of electrons don't bond. We call those lone pairs. Single electrons bond. We are going to predict bonding capacity based on the singles. Lithium. One S, 2s, 2p. 1s, 2. So we've got to do our spin up and our spin down. That ends our lowest energy. Our second lowest energy is 1s. And there's 1 electron. Spin up, and I ran out of my electrons. I wrote in 2p just to show that those are going to be empty. There's no electrons in those orbitals, or 3s, or 3p, or 4s, or 3d. You don't have to show the empty ones. Okay? But sometimes you may draw more boxes than you need and just leave them empty. You don't have to erase them. This is all ground state configurations. You pump energy in, maybe you can move that 2s electron to 2p, but then it's going to fall back down, emit radiation, and you could use what we learned energies h nu to make predictions on those wavelengths. So that's our electronic configuration in orbital diagram. If you ever can't remember the fill order through the table, or you're really low and it's getting confusing, I want to show you a shortcut or a guide to knowing the fill order. We're going to need this for the removal order, so it's going to be more important for a couple lessons ahead when we take electrons away. We'll vary this a little bit. So filling, you start with 1s. And then I'm going to lay out all the allowed orbitals, and all the diagonals tell us the order they fill. So 1s, there's 2s, there's 3s, 4s, 5s, 6s, so we keep going. The p orbitals don't start in the first shell. They don't start till the second shell. D's don't start to the third shell. F's don't kick into the fifth. Sorry, the fourth. Writing and talking is more difficult than it looks sometimes. Then F, after F, they go alphabetic. And we're never going to see G's, but I put it in. The fill order is the diagonals. So 1S is where we fill first. Then we fill 2S, 2P, and 3S. So right here. Next, aluminum 3P. And then we jump down to the next row, 4S. We've got the calcium, then we're in scandium, we're finally in the Ds. And that's that diagonal. And I'd have to fill in some couple more rows to do the next few diagonals. You don't always have to fill everything in, so 6S, 6P, 6D, and that lets me get my next diagonal in. So the fill orders all the diagonals, but we don't remove electrons the same way. We actually remove them from the bottom up. But that's a future lesson, our next lesson. That can help you, but you don't really need it if you can snake your way through the table properly. Okay? But if you ever got, maybe more in post-secondary, you're trying to deal with this F block and where it fits in the table and you're having trouble, that's going to help you deal with the F block. Last slide of the day, we've covered a lot of the build-up principle already. Just one more shortcut, simplification. Electronic configuration, you can use the previous noble gas as a core and just build the electronic configuration on top of the next noble gas and make things even quicker and shorter. So I'm going to do sodium, chlorine, and cesium to end. So to get started, I have to find sodium in my table and then find the preceding noble gas. It's going to be a row above it. It's not going to be the same row. So sodium is in period 3, atomic number 11. The preceding noble gas is not argon. That's after it. It's neon. So we're going to build on top of neon. We're not even going to write neon out. We're going to assume that you know how to do that. And you're just going to do square brackets neon. That would represent the electronic configuration of neon, and then we're going to keep going. We're only one after neon. 4, S, and we're 1 over. So sodium has the electronic configuration of neon, and then 4s1 for its valence electron. Things are getting even faster. So we went from doing 11 sets of quantum numbers to a noble gas and the valence. Chlorine, atomic number 17. We're going to have to go way back and find its noble gas, preceding noble gas. So I fixed my error with sodium. I just wrote, I was 1 row down going too quick, but it is in the 3rd row. Chlorine also has neon as its preceding noble gas. So chlorine's atomic number 17, 10 is the preceding one. We got a little bit more to build on top of that. So I need to be careful. I am in the 3rd row. So we've got sodium and magnesium. That's 3s2. And then chlorine is 1, 2, 3, 4, 5 over in the P block. So 3s is filled, 3p is 5 over. And that's the 7 valence electrons that the chlorine atom has. We'll deal with chloride again in the next lesson. Or sodium plus, we'll deal with that, removing and adding the next lesson. Last is cesium. Way down, atomic number 55. Preceding noble gas is atomic number 54, xenon. And we don't have a lot to write here because we're at the far left. S block, 6th row, and S and P blocks, the number corresponds to the row. D is 1 off, F is 2 off. So 6S, first one, 6S1. Double check my 6. Yeah, I'm in the right spot. So that's the electronic configuration. So that's most of quantum mechanics done, except for removing electrons. My last diagram, I think I've talked about this, hopefully enough, but this will be a visual in your notes. It's nicely labeling all the pieces of the periodic table by what subshell you're in. So again, we've got this mislabeled helium that probably would go much better over there, but it's a noble gas, so it tends to go in group 8A. 1s, 2s, 2p, 3s, 3p, 4s, and then we hit D's for the first time, and D's are 1 off. It's the 4th row across, 4th row down, but it's 3. When you get to F, it's 2 off. So the F kicks in the 6th row. So now homework hopefully maybe can start getting a little faster, particularly once you get the patterns down. So that is most of quantum mechanics for high school.